All right, we have a small gathering. Welcome everybody. Am I in? Yep. Right, so we've gathered to hear what Pi has to say today, and she's going to talk about the work that she's done during her visit. You've been here for a year?
Yeah.
I think Pi's been the most productive visitor we've ever had. I actually didn't meet her very immediately. She arrived. She did a bit of work with Editors, who should be here. So they met, had a bit of a discussion. So the first time I met Pi, she came in and we had a research meeting, and she had outlines for 4 journal papers in the first meeting, which seemed to me to be pretty good. I was pretty happy with that sort of thing. I gave her back the 4th paper this morning, which we're going to submit possibly tomorrow.
Yeah. So
all of that prediction has actually come to pass. So it's been a very, I don't know, you'd call it spectacularly successful visit. We've had 1 paper accepted, 1 paper rejected, but we're going to resubmit it, and 1 is under.
2 is review.
So the second one's been so there's 2 under review, and this 1 is about to be submitted. So we're pretty happy, and there's even some future work arising out of some of this stuff, which looks pretty interesting as well. So I don't know how long you've got. A clock? No, clock. Righto, see if you can fit it into an hour. This is Pi. Oh, from Beijing Institute of Technology, visiting. And she's got very neat handwriting.
Yeah.
In English. Yeah, we're going to look at this. I'll just gather a little bit. Yes. All right. Does that work?
No.
Okay.
Thank you so much for coming to this seminar. And the topic of today's seminar is about JAMA detection, characterization, and mitigation for GNSS receivers. And I will present a summary of all the work I have done during this visiting year. This is the content. First, I will give the background knowledge of GNSS jammers, and then talk about jammer classification and common jammer countermeasures. Considering the special properties of GNSS jammers, several techniques in terms of detection, characterization, and mitigation have been developed, and I will give the main ideas and results of these techniques. Global navigation satellite systems include GPS, Galileo, GLONASS, and Beidou, presents an important infrastructure to our society. They provide positioning and timing service to numerous applications, including the power grid system, banking operations, transportation systems, and other communication systems. With GNSS entering more in the core of many applications, ensuring its integrity becomes more and more important. The GNSS signals have been designed to withstand a certain level of interference resistance. However, due to the weak received power level, they are still vulnerable. Unintentional interference, such as signal harmonics, generally comes from other telecommunication systems in the GNSS frequency band. Besides unintentional, there is intentional jamming. It is generated by jamming devices like personal privacy devices, which deliberately transmit powerful signals at the GNSS frequencies. Although these devices are illegal to sell in many countries, including Australia, United States, and other European Union countries, we can still purchase this device on website costing only few tens of dollars. These are 2 examples of intentional jamming. The first objective is to attack others' use of GNSS. For example, South Korea had experienced several GNSS outages since 2010 due to North Korea's ability to jam GPS signals with a radius of 50 to 100 kilometers near the border. The other objective is to defend one's own privacy. The famous example is in late 2009, a truck driver who periodically passed close to the New Liberty International Airport used a GNSS jammer to prevent his company from tracking his position. These low-cost and portable devices present a serious threshold to the utility of civilian GNSS-enabled systems. A common scheme of GNSS receivers includes several stages: front-end acquisition, tracking, and position. The general impact on these different stages are listed in this table. Different degrees of performance degradation may be experienced based on the jammer power and spectral characteristics. For example, the jammer can lead to several elements in the front end working outside their normal region. And wrong Doppler and delay estimates may be obtained in the acquisition stage. With the increase of jammer power, the tracking loops may experience loss of log of the signals and then lead to the discontinuity in positioning and timing results. To better understand the jammer characteristics, a lot of work has been done concentrating on jammer classification. From the viewpoint of signal characteristics, they can be classified into 4 classes: continuous wave signal, single sawtooth chip signal, multi-sawtooth chip signal, and chip with frequency bursts. The instantaneous frequency characteristics of these 4 classes jammers are shown in the right figure, indicating the rapidly time varying features. These jamming signals can be broadcast by a large variety of jammer devices, including 3 groups, based on the device characteristics. Generally, in order to ensure the integrity of the GNSS, the receivers should be equipped with some anti-jamming techniques. The first step is to detect the presence of jamming signal, and after declaring the presence, a characterization method should be applied to provide the signal's characteristics, which are then used by the mitigation unit to excise the jamming signal from the received data. This map shows the common jammer countermeasures in terms of detection, characterization, and mitigation. Detection techniques include hardware indicators such as AGC level, noise floor level, pre-correlation methods using statistics and other transport domain analysis, post-correlation methods such as CNR and other measurements. Due to the time-varying nature, characterization is generally based on time frequency-based methods. Mitigation techniques can be characterized into 4 groups: inertial aiding, spatial filtering, time frequency filtering, and vector tracking. In inertial aiding and vector tracking techniques, the minimal clear-to-noise ratio in acquisition and tracking units can be lowered. And then, in this way, the receiver can still operate in the presence of relatively strong jamming condition. With the spatial filtering and time filtering, frequency filtering, the jamming signal can be mitigated before entering the receiver. Till now, I introduced the background, the impact, and the classification and common countermeasures. Now we need to pay attention to the major issue when we attempt to detect and mitigate the GNSS jammers. Most jammers used in civil context broadcast frequency modulated signals with an almost periodic behavior. The swap periods are typically around 10 microseconds, whereas swap ranges are usually in the 10 to 40 megahertz interval. Compared to the generally considered normal and wideband interference, these fast frequency varying signals are more difficult to be tracked, especially the shorter swap period. The more difficult it is to mitigate the jammer. So recent researchers considered techniques specifically tailored for these jamming signals. Moreover, pre-correlation methods are considered, which work at the early stage of the receiver chain. In this stage, the useful GNSS signals are entirely buried below the noise floor and only have marginal effect on the jamming monitoring unit. In this way, the receiver can raise an early warning and then mitigate the interference in the received signal. Due to the non-stationary nature, the single domain techniques such as the time domain blanking or frequency domain filtering become ineffective. Then the time frequency-based techniques are introduced. Unlike the noise component, which exists across all the frequencies in the time frequency plane, the jamming signal generally concentrates within a small region in this time frequency plane. So this property makes these techniques very efficient for dealing with non-stationary jamming signals. Now we move to the fourth detection algorithm, which is based on time frequency analysis and statistical inference technique. Various time frequency tools can be used to represent the non-stationary signal, such as linear transform, short time Fourier transform. Another class of these tools are the quadratic ones, which have the high resolution and good cross-term separation. Here we use the pseudo Wigner-Ville distribution to provide the IF estimation based on TF ridge detection. This flowchart shows the specific steps in this algorithm. Besides the received signal, we also need to use an interference-free reference signal. As I stated previously, in the pre-correlation stage, this signal, in the absence of interference, can be regarded as noise component by ignoring the weak useful signal. So, since the noise exists over all the time frequency plane, the IF estimates also vary randomly. However, in the presence of jamming signal, this is not the case, because in the realistic IF function of a jamming signal usually have a certain geometric shape. So after we obtain the IF estimates from these two signals, we can introduce a statistic inference technique concerning variance, that is two population F test to the two variance of the IF estimates. And this test statistic follows a F distribution, which can be used to determine the detection threshold for giving false alarm probability. And then we can compare this test statistic with this threshold to determine the presence of interference. And extensive simulations were performed to verify the effectiveness of this proposed method for detecting various classes of jammers. And this figure shows the detection probability with respect to jammer to noise ratio for detecting the 4 classes of jammers as I stated previously. Now I will introduce the second detection algorithm based on statistic analysis in time frequency domain. Now the short time Fourier transform is used as the time frequency tool due to its linear property. The canonical form is shown in this equation. instead of processing the whole signal at once, the STFT perform FFT based on a block-by-block basis. In the pre-correlation stage, the received signal can be regarded as noise component in the absence of interference. So, from the statistic viewpoint, the real and imaginary parts of STFT results can be approximately regarded as independent Gaussian variables. Then, the goodness of fit test, which is used to indicate whether a specific model for a population distribution fits the observed data, can be applied in time frequency domain for detecting the presence of interference. And this slide shows the specific steps for GOF test. In the first step, we compute the spectrogram, which is the square modulus of SGFT of a piece of baseband samples. And we, for each frequency slice, we compute the observed PDF. The next step is based on the noise component, we compute the expected PDF. And then in the final step, we use this observed and expected PDF to compute the test statistic using this equation, and then compare the significance level of this test statistic with a predefined one to complete the whole detection process. Actually, the canonical SGFT samples with time distance shorter than the window length are correlated because the samples used in the adjacent blockers are overlapped. And this will lead to the degradation of false alarm performance, which is undesired in a detection problem. Basically, in the STFT computation, the blocks can be both overlapped or disjointed. So in order to eliminate this undesired degradation, a solution based on block-wise STFT is also proposed. So we propose the similar algorithm based on both the canonical and block-wise STFT with different detection and false alarm performance. Simulation results shows that these two methods can improve the detection performance for narrow and wideband interference in low GNR environments compared to the existing test directly applied to time domain samples. And this figure shows the detection probability in terms of GNR for CW and chip signals. And for a given GNR, the detection probability is clearly improved. Till now, I introduced two detection algorithms, and we move to characterization. Typically, large sweep bandwidth of the jammers within a short time make it difficult to accurately characterize the IF with a view to excising them from the received signal. The left figure shows the IF estimation errors when we apply the conventional time frequency range detection. As can be observed, there are impulsive nature IF estimation errors, which definitely would degrade the subsequent mitigation performance. So we want to address this estimation error issue in the characterization stage. Based on the previously modeling results, most of the jammers belongs to class 2. These jammers broadcast unidirectional or bidirectional chip signals, which means that they just have one sawtooth function for describing the IF. That means it's a simple mathematical model. So we propose an improved characterization algorithm based on short-term ring entropy, specifically for class 2 jammers. The short-term ring entropy, which is modified from the classical channel entropy, is initially proposed for estimating the instantaneous number of components of a multi-component non-stationary signal. if we apply this parameter into general characterization, these two figures shows the instantaneous number of components and the IF turning points. It can be also observed that these two parameters has a one-to-one correspondence relationship. So we can apply this parameter to provide information about the turning points in the IF function, and then use these values to generate the improved IF estimates. In order to exhibit the advantage of this algorithm, the improved IF estimates are used by the notch filter-based mitigation method for gamma removal. And these two figures shows the cross-ambiguity function obtained in the acquisition stage. In the left figure, when applying the conventional algorithm, no visible peak can be observed, which means that the Doppler frequency and code delay estimates may be incorrect. However, if we apply this proposed algorithm, a clear peak emerges from the low noise floor. So, based on these two figures, we can say that this characterization algorithm can eliminate the impulsive IF estimation error problem. The next algorithm is about adaptive algorithm for time domain windowless in smooth pseudo-Wigner-Ville distribution. For representing non-stationary signals with nonlinear IF characteristics, there is an inevitable trade-off between time resolution and cross-term separation. Generally, cross-term and noise components should be suppressed using a long window length. However, a short one should be used to track the rapidly changing signal. So, in order to realize this trade-off, we need to develop an adaptive algorithm for the time domain window based on the highest energy concentration criteria. And using this criteria, we obtain the time domain window length, which can be adjusted based on the IF characteristics. This slide shows 3 SPWAD of a nonlinear chip signal using a fixed short, long, and adaptive time domain window length. The first figure exhibits good resolution at the expense of worse noise resistance when we use a short window length. On the contrary, a long window length leads to worse resolution and low noise floor. And the third figure, we use adaptive window length, and it shows that the adaptive one outperforms the two fixed ones in terms of the overall time frequency performance. After we obtain the characterization results, we hope that we can use these results for the final general mitigation. Generally, the inference mitigation can be relies on several operations. For example, the time domain subtraction technique can reconstruct the time domain samples using the IF estimates except for only a constant phase offset. The subspace projection technique can realize mitigation by constructing a subspace orthogonal to the general subspace. And a notch filter can also be used by adjusting the notch with the IF estimates. In the case of accurate IF estimation, all the techniques are effective. The time domain subtraction and subspace projection techniques can provide almost upper bound correlator SNR, which is a very important indicator of the receiver performance. However, the notch filter-based technique would simultaneously excise a small portion of useful signal when it excises the jamming signal, and this would lead to slight degrade correlators and R. However, accurate IF estimation is not practical. So, in the previous literature, there are several assumptions of IF estimation error. For example, constant estimation error, the maximum tolerable estimation error, the IF or instantaneous phase estimation errors with a zero-mean Gaussian model. In realistic situations, the errors may originate from noise, interference, and frequency discretization. However, for GNSS jammers, due to the very short sweep time and large bandwidth, as I stated previously, there are inevitable impulsive nature IF estimation errors, which are different from the previously assumption in the literature. So this is the major concern of the mitigation techniques considering the GNSS jammers. And there are three possible solutions. Due to the impulsive nature IF errors, the phase errors exhibit step-like shape due to the accumulation operation. So a segment-by-segment correction of the average phase residue can be applied in the time domain subtraction technique. And in the presence of impulsive nature frequency estimation errors, the general subspace projection technique becomes ineffective. So we can decrease the sample size in each projection operation. That means partitioned subspace projection technique to solve this frequency estimation error problem. Also, this impulsive frequency estimation error would also lead to impulsive jammer residue in the output of the mitigation unit. So the passive interference is generally handled by a pass blanket, so we can apply a general mitigation unit followed by a pass blanket to solve this impulsive residue. This is all the content of today's seminar, and I hope that this can help you better understand the general content of GNSS jammers. And if you have any question, please feel free to ask me. And thank you so much again for coming.
You didn't have a lot of results there.
Yeah.
There was a lot more results than that. Questions?
I have a question here that's related to that. Because if you want to detect the interference, so
yeah.
you need the signal you receive is only an IF signal.
Yeah.
So what is
hold on. She uses IF to mean instantaneous frequency.
Yeah.
Yeah, I know instantaneous frequency. I know about it.
Are you using
No,
it?
I know. Yeah. Okay. So really, you get the sample data from the fontaine.
Yeah.
So if the jammer period is very far, like 10 microseconds.
Yeah.
So what is the minimum sampling frequency you need to detect this? And how many bits you need from the ADC to detect? Because if you have only like 2 bit
Yeah.
ADC.
But actually now I only consider the ideal condition, which do not consider the effect of ADC, because from the theoretical aspect, we assume that we generally ignore the ADC effect on the detection problem. Yeah. I know, I understand that.
Yeah. I think we have discussed this, but it was a long time ago.
Yeah. I remember.
Yeah. Just more than I know.
Because I do the real experiment with this program. I try to generate the squid jammer using the spiral and using the not map receiver to receive.
Yeah.
So if the not map receiver, when it has like 4 bit sampling, So if the jammer is very the jammer power is not strong enough, so the receiver still work well. You
Interestingly,
don't see any effect.
The results for tomorrow's paper, is about strong jammers, but most of those results there, you see the JNRs were all negative, right?
Yeah, yeah.
So that's not actually going to do much with the ATC.
Yeah, for detection, we generally consider weak jamming signal when we want to improve the performance, and
yeah. I mean, strong jammers are easy to find by other means, right? So this is all operating below north.
Oh, okay.
One of the questions that I always have, I've got a couple of questions, but one of them is how weak can the jammer be and still be of consequence, given that what you're doing, is you're doing the correlation with the with the code, you're doing despreading, and the jammer is not going to be despread.
Yeah.
So how big can the jammer be, and you still have to care about it?
Ask your own student. From what I saw of his APR this morning, that this is his area. Anyway, you go.
No, but this is application specific. In GPS, how weak? Because in GPS you're doing despreading for the GPS signal.
Yeah, you know the answer to this.
Yeah. In today's paper, actually, I have a value. It's in the literature state that the JSR exceeding 40 to 50 dB can prevent a receiver to obtain the petition. If the JSR is below this range, I think maybe only degraded performance would be experienced, not.
Yeah, okay, I'm going to butt in. Okay, so you're looking at there where the JNRs would be negative, right, down to minus 10 dB or something.
Yeah,
this is
on that scale.
But this is our area of speciality because what we're doing is locating jammers, like what you're talking about, right? So the idea is that if you've got a network of stations that are looking for jammers, in order for you to do a good geolocation, you may have to detect a weak one. Even though it's not really affecting where you are, it's going to be affecting someone else some way away.
Okay.
So in order to do your geolocation, you have to be able to detect weak jammers. So this stuff is quite important for that system. So the stuff that we're doing with GPSat systems and the absent edges.
So it's not a jammer to the necessarily to the receiver that you've got. It's a jammer to some possibly somewhere else.
So these techniques would probably be in one of these stations that GPSat systems is. You know, they could use it.
Yeah.
The other question that I have is with respect to, you say the jammer is non-stationary.
Yeah.
Now, the jammer could be moving in space.
Yeah.
Or it could be transmitting a non-stationary signal.
Yeah.
I didn't get a very good sense of, I saw that you're using the IF, so you're assuming that the frequency is changing in time.
Yeah.
So the jammer at any one point is assumed to be a continuous wave, a single tone. Is that the premise?
That's how much they are. Yeah, the commercial jammers.
The class 1.
Are you just asking about Doppler effect on this?
No, I'm just wondering where the non-stationarity comes from and what it is.
It's deliberate, which means that
So the jammer, from what I saw, the jammer sweeps the frequency using a single tone.
Yeah, it's a wide band, but instantaneously narrow band. Yeah.
And do they all have linear frequency characteristics, or?
Most of them have these IF characteristics based on the modern results, because the researchers buy a lot of jammers and then characterize the IF properties using the spectrum, observing the spectrum and then obtaining the results, and then have these modeling results. Yeah.
Some science.
The most popular one.
The most popular is I think the class 2.
Class 2.
Most jammers belongs to class 2.
So, but in space, it's not really
Yeah, because
considered to be moving, because it's going to be moving maybe with a person. So you can assume that it's not really moving. Am I correct?
It's normally in a car. People just, like a vehicle will jam its own GPS, so you don't know where it is.
Yeah, so this is talk about pseudo context.
All right.
Yeah.
Okay.
So, do you have any implementation with the detection?
Sorry.
Did you have any real implementation
Real.
to detect the jammer?
No.
It's all like that.
Yeah, only in matter.
Yeah, because so how long does it take to detect? How long does it take to calculate the instantaneous frequency?
Yeah, that was a question I think we have to put into the paper tomorrow. I've got two things then to talk to you about. That's one.
Yeah, because the thing here is that if the jammer period is very fast,
Yeah.
so the number of samples you have is very short, and how long does it take for you to detect this?
So if you want to have a better detection performance, you can use longer sample size.
Yeah,
I
but
mean,
the thing is that the jammer is changing
very fast,
Yeah.
right? So within a general observation window, there are usually several sweep periods.
Yeah.
So you can detect based on this observation.
If I'm correct, yeah, I know it's correct if the period of the jammer is like an instant period, like a constant period.
Yeah.
Talking about the rate of change of the frequency of the jammer.
Yeah.
And also how long the sweep is. Like that period there.
Yeah.
Well, your most important parameter is the rate of change. The faster it is,
Yeah.
the smaller your block has to be. Otherwise, you can't assume that it's a single tone.
Yeah.
That's what it comes down to. But there are other the time frequency distributions
Yeah.
have different performance depending on what the characteristics of the signal is.
Yeah.
So if you have a linear chirp,
Yeah.
what might be best is different to what if you have a quadratic chirp, for example.
Yeah.
So have you looked? There are other methods. For example, just a simple NVDR.
Yeah.
You instead of using the short time Fourier transform,
Yeah.
you use an NVDR on short windows.
Yeah.
They can be overlapping,
Yeah.
and that can actually work well. There are a lot of papers on time frequency distributions.
Yeah. Yes. Yeah. So.
Eliza's done some of that work as well.
Yeah, we looked at this in bats. Now bats are different kettle of fish because their signals can be quite horrible, and they're not single tone anyway because they can be multi-tone chirp at the same time, and they're non-linear anyway.
Yeah.
So.
There is a problem with the hardware when you generate. It never had like a fixed period for the signal.
But it's less an issue of what that rate of change is how long it takes you to. Basically, you're doing a bit of post-processing in the receiver. It's not really real-time processing because you block. So it's how long that processing takes, which is a bit of an issue. Okay, anyone else? All right, thanks, Pi.